This is our recitation 8, and this problem will be about coaxial cable. So you have a conducting cylinder with radius A. This cylinder is infinitely long, and there is current I flowing in this cylinder. And this current I is uniformly spread over the cross-section of the cylinder. This conducting cylinder is surrounded by conducting shell with inner radius B and outer radius C. And you have another current, the same magnitude, but opposite direction. So the current is flowing in this conducting shell, also has magnitude I, but it has direction opposite to the original current. And this current I is also uniformly spread over the cross-sectional area. What we need to find the magnetic field everywhere, inside and outside this coaxial cable. And I remind you that this is infinitely long cable, which means in reality that we will work far from the edges. We will use Ampere's law to find the magnetic field everywhere. And according to Ampere's law, integral over closed loop of B dot dr is equal to mu naught, which is constant, times current enclosed by this loop. Well, obviously we have different regions here, and the first region that we will consider will be R less than A. For R less than A, we will draw a loop of arbitrary radius R. This loop has arbitrary radius R that is less than A, and I will be working with the left-hand side of Ampere's law. The lines of the magnetic field created by this current are circles, and the magnetic field will be tangential to this circle at each point. So the left-hand side, B dot dr, is simply integral of B times dr. From symmetry, I understand that B is the same at each point of this loop. So I can take B out of this integral. Integral dr is, B is still here, integral dr is circumference, 2 pi r, and this is equal to mu naught. And then I need to write current enclosed by this loop. So how much current is flowing that is bounded by this loop? First, I need to find current density. I remind you that current is integral J dot ds. So current density for this cable J will be magnitude of current density, will be current I divided by cross-sectional area of this wire, which is pi a squared. This is current per unit area. So what I put here is current per unit area, I over pi a squared. This is J, current density. And now what is the area bounded by this loop? Area bounded by this loop is pi r squared. This is, let me use different color, this is current per unit area. In other words, it is J. And what I have here, I have area bounded by this loop. So my equation is B times 2 pi r is equal to mu naught I over pi a squared, and then area of the loop pi r squared for r less than a. Now we solve this equation and find the magnetic field. What will be the magnetic field in this case? B. We find magnitude. Let me simplify it. So pi and pi cancel out, then r and r squared here. My final solution for the magnitude of the magnetic field is mu naught I divided by 2 pi a squared and r. This is magnitude. What will be the direction? So if I have my current, now let's find the direction. So I will draw the side view of this cylindrical wire. Let me use the same color. Let's start again. I'm sorry. One more time. Was it orange? Was it, what is this? Orange or yellow?
Looks like an orange.
Orange. Okay. So now let's find the direction of this magnetic field. So if I draw the side view of this wire, this is my wire, current I is into the page, then what will be the direction of the lines of the magnetic field inside of this wire? You have to use right-hand rule to find the direction of lines of the magnetic field. I use my left hand again. Why? Because you see my mirrored image. So it's funny. I put my thumb along current. So current goes into the page. This is my thumb. And now I bend my fingers, and my fingers show the direction of the lines of the magnetic field. We are at R less than A. We are right here, and the lines of the magnetic field will be circles with the direction clockwise, as I just showed with my hand. One more time. You take your right hand, you put your thumb along current, and you bend your fingers, and your fingers show you the direction of the magnetic field. So we found the magnitude and the direction of the lines of the magnetic field. So in this case, I can put here clockwise. Okay, now we move to the next region. We were at R less than A, and now I will I will draw another loop. Now we are at R between A and B. So that was 1. Let's put 2. R is now greater than A and less than B. We will use again Ampere's law. Integral B dot dr is B integral dr. Left hand side of Ampere's law will be the same, with the same logic that lines of the magnetic field are tangential at any point, tangential to this loop. So we simplify the left hand side of Ampere's law, and we write B times 2 pi r, where r is arbitrary radius between A and B. So B times 2 pi r is equal to mu naught times current enclosed by this loop. But what is current enclosed by this loop? It's current I. So we put I here. What is the magnetic field? The magnetic field is mu naught I divided by 2 pi r. And the direction of the lines of the magnetic field is clockwise again, with the same logic. So I can just add it. If I draw again this wire and current is into the page, I again can bend my fingers, and the lines of the magnetic field, I used pink. Let me keep the same color for the lines of the magnetic field. So here's my wire. And then here are the lines of the magnetic field. the direction is clockwise. Why? One more time. Because, let me just put it here. Because I put my thumb, current is into the page, this is side view, I put my thumb along current, I bend my fingers, and yes, it is clockwise, we did it right, we did it correctly. Next region that I'm interested in is R3. And for 3, I will need more space, so I'll start here. 3. Now, R is greater than B, but less than C. What will be the magnetic field? Left-hand side, where is my loop? Now my loop, let it be pink. So this time, this is my loop of arbitrary radius R, and R in this case is between, this is my little r. It is greater than B and less than C. The question is, what is current enclosed by this loop? That's what we need to figure out. Current enclosed by this loop. Left-hand side of Ampere's law will be unchanged. So I have B. If I write here, will it be clear what I'm doing? So I'm in this region. And now I write B times 2 pi r. This is the left-hand side of Ampere's law. It is equal to mu naught. And now we have the most interesting part. We need to find out what is the current enclosed by this loop. One part is easy. Obviously, current I is enclosed by this loop. So I open parentheses and I put I. Now we have another current I in opposite direction. And just part of it is enclosed by this loop. So, which part? That's what we need to figure out. I have this cylindrical shell. Why don't we first find the current density within this cylindrical shell? So we found current density for this cylinder, and now I will find current density for cylindrical shell. I will use orange, and I will do it right here. So, what is current density for the cylindrical shell? It is current I divided by area of this cylindrical shell. What is area of this cylindrical shell? Outer radius is C, so it is pi C squared minus, I need to subtract this whole, so it is minus pi B squared. J is current density for the cylindrical shell. Okay, so now I know current density and I can figure out what will be the current enclosed by this pink loop. But before we start writing it, let's figure out the sign. Look, so current I is into the page or to the right. On this picture, it is to the right, and this current is to the left. So obviously they are in opposite direction. And I need, if I treat this direction as positive, then this direction will be negative. So I already put I with plus. Now I need to put minus for the portion of current that is flowing in opposite direction. Now we know J. J is I over pi C squared minus pi B squared. Current density, current per unit area, times area enclosed by this pink loop. What is this area? It is pi little r, where r is this arbitrary r, pi r squared, and I don't forget to subtract the middle, minus pi B squared. And we close the parentheses. We did it. One more time, the same logic. Left-hand side is not changed, B times 2 pi r, left-hand side of Ampere's law, mu naught, and then we summarize all currents bounded by our loop. It's current I that is flowing to the right, and it is part of current I that is flowing to the left. Which part? Current density, current per unit area times area bounded by this loop. Now we can solve for the magnetic field. And this will need some space, so I need to erase a little bit. I will erase here. Now we will simplify the right-hand side. I will put this arrow here for you to see that I continue writing here. So I factor out current I, and now we will bring this expression to common denominator. I have pi c squared minus pi b squared minus pi r squared minus plus pi b squared, and I divided by denominator pi c squared minus pi b squared. Pi b squared cancel out. So my final, finally, my right side of this equation looks like mu naught I, pi c squared. Can I cancel pi? Pi. Can I do that? Yes. So I have pi, no pi. I have c squared minus r squared divided by c squared minus b squared. And now we will find b. So what will be b in this region between b and c? It will be mu naught I divided by 2 pi r, and then c squared minus r squared divided by c squared minus b squared. In the direction will be clockwise, as we just discussed. So the magnetic field has magnitude and direction. We found both. And we have one region left outside of this cylindrical wire. So the last region will be R, this is 3, and now 4. R is greater than C, and that's the most interesting part because this is coaxial cable. Now my loop will be arbitrary R that exceeds C. This is my loop. Left-hand side, any changes on the left-hand side of Ampere's law? No changes. It is B times 2 pi R is equal to mu naught, constant, and then current enclosed by this loop, which is current I that is flowing to the right, and then current I that is flowing to the left, and it comes with minus. So magnetic field outside of this coaxial cable is 0, as we expected. So now we know magnetic field everywhere. Problem solved.